All right. So last time, I'm actually going to switch over my cameras here. See if that works. Keyboard shortcut not working. Okay. You can't see that. All right. Hang on. I don't think. Maybe you guys can just make that out. So we ended last time right here. We asked about the number of non-negative integer solutions. Did I post my notes for you guys to Canvas? My lecture notes? Hang on, I've got Canvas pulled up.
I'm also checking real quick.
I did not. All right, later today when I go out there, I will, some of you might have picked them up earlier. I had the files link open earlier in this semester, but you know, that's not what I'm going to rely on. I'll post them. They are, as I told you guys at the beginning of the semester, not good, and they get worse as the semester goes on. So the main reason I will post them is just because it'll be easier for you to follow along with the questions I'm asking and things like that, not because I think they make a good lecture replacement. They really don't. There are typos still. There's a grammatical inconsistency in today's lecture. I mean, hopefully, obviously there's going to be at least one I'm talking, but I mean, in the part that we're going to cover today in print. So let's see, we finished that one up. And actually, I think it was Alex asked about partitions of an integer at the end of the last class. It was somebody who did. And that's actually the next question is about partitions of the integer 5. So how many partitions are there of the integer 5? We're actually going to answer the question, at least partially, how many partitions there are of any integer. So 5 is going to be our k, and we're going to look for a k in some generating function. Oh, there, I lost it. Focus. Come on. Like I said, this is kind of annoying. I shouldn't have moved the paper so soon. Come on. There we go. Sorry about that. So anyway, we're going to answer the question how many partitions there are. And what we're doing here is we're going to set up some generating functions, like I said. And this is going to be real similar to what we were doing with the different colored balls. And they're just going to answer these occupancy problems. And so for partitions of the integer, we need to think about letting the terms in a generating function represent, for instance, how many ones we can have. So let's see. So if we have, I don't have a good letter for it, I'll just call it G1 of x would be equal to 1 plus x squared plus x cubed plus x to the fourth, and so on. And this would represent having 0 ones, and this would represent having 1 1, 2 1s, 3 1s, and so on. And G2 would represent, so let me explain. So like, for instance, we're finding the number of partitions of the integer 5. So there's only one way to partition the integer 5 using all ones, and that's the coefficient of x to the fifth. There's no ways to do it using just 4 ones, but we don't have to worry about that because this is not the only piece of the puzzle. So we're going to say, well, what would it be if we used 2s? Well, I could use 0 2s, or 1 2. And here the 2 in the exponent, let me get a couple of terms down here. So the weight of the number of 2s, so the weight of 0 2s is 0, x to the 0. The weight of 1 2 is x squared, and so on. And so if you just were to multiply these guys together, you'd see why you could never do it using 4 1s, because nothing you're multiplying your x to the 4 by in the 2's generating function is going to get that to be x to the fifth. It's either not going to be enough or it's going to be too much. And the same is true for 3's. Technically, these are infinite series. 4's. So, like I said, technically these are infinite series, but if we're only looking for the integer 5, then we're looking for the AK term or the GK, depending on what we're doing, but we're looking for A5 in the generating function g of x equals g1 times g2 times g3 times, actually, so on forever. Except we don't have to worry about so on forever, because anything after G5 is going to give us something that is larger than the x to the fifth term. So this would be, the AK x to the k. So we want to find the x to the fifth term in G of x, which we can do just by multiplying this guy. He is, well, there's a couple of ways we could do that, I suppose. But for this one, it's actually fairly easy. We can just kind of multiply it out. So we get 1 plus, there's only one way to get x, right? It's this x times those 1s, plus how many ways can we get x squared? No ways with this x, but so we just get the 2x squared and then all 1s, or 1x squared and then all 1s. So 2x squared. And how many ways can we get x cubed? We have x cubed times all 1s. We have x times x squared. We have x cubed times the rest 1s, so that's 3x cubed. And then how about x to the fourth? I think it's 5x to the fourth and 7x to the fifth, and so on. Now, I did that by directly multiplying them out, and that's fine if you just need to go like find the coefficient of the x to the fifth term. Of course, if you wanted the coefficient of the x to the 83rd term, you might want something a little better than that. So what we have here is that G1 equals 1 over 1 minus x, and G2 is 1 over 1 minus x squared, and G3 is 1 over 1 minus x cubed, and so on. So in general, the number of partitions of K is the coefficient of x to the K in G of x equals the infinite product of 1 over 1 minus x to the m. And this is what I was promising you, is at first you're like, oh, hey, we've got a formula then. But notice what I just did when I was finding the number of partitions of x, or sorry, the coefficient of x to the 5 to find the partitions of the integer 5, is I was looking at which of these exponents added up to 5, which means I was just doing the partition problem over again, right? I was saying, oh, 5 plus zeros, that works, and 4, that doesn't work with anything. That 4 plus 1 works, so 1 plus 4 plus zeros works, and so on. And that's how you get that 7 there, which is really just listing them like we would do before. Apparently I missed some. What did I miss? I get all ones. Oh, that's 7 of them. And that's essentially what we just did by playing with the exponents. So, you know, the generating functions, they help, but they only help so much. Usually, somebody asks at this point, and I'm going to assume it's because you all have your mics muted politely, but usually somebody asks how we got this. And what we're doing is we're using the coefficient of the generating function to represent the thing we're looking for. And so then we're taking these little sub-generating functions here and using them to represent the different cases. So like I said, this represents the cases, the number of ones in your partition. And this represents the number of twos in your partition, in that we can have 0, 2, 1, 2, 2 twos, 3 twos, except you can't really, not if you're going to stop at 5. So as a matter, and so you see here's the partition with 2 twos. That's the one where x to the 4th paired with the x. Now, not everything got used, like that x to the 4th. It's no partition has exactly 4 ones in it. No partition of the integer 5 has exactly 4 ones in it. So that one actually doesn't contribute anything to this final, well, to this. But it would if we were asking the question how many partitions of the integer 6 there were, because then we could get it like this. That one would be one of those. So that's where this is coming from. We're using in this product here, we're saying that we can pick the number of ones, the number of twos, the number of fours, the number of 86s, and we don't, that may not contribute to the specific A5 we're looking for, but for some combination, if I said, well, I want 3 ones and 3 twos and 2 threes and so many, and went through and picked, and then that term, when I multiplied it out, that would be a part of the partition. That would be one partition of some particular integer, but it would be the one that was the sum of those exponents. And if I looked at just that coefficient that it would be made up of 1 for each one of those ways that that product worked. So we're using the fact basically that when you multiply power expressions, you add the exponents to say, well, then 3 plus 2 plus 3 is some partition. It's one particular partition of 7, for instance. So let's answer a similar question. How many partitions of K contain only distinct parts? What do we mean by distinct parts? We mean that an individual number can only occur either 1 time or 0 times. It's not distinct if it occurs 2 or more times. So that changes what our G1, G2, G3 look like. So we get G of X equals 1 plus X for the number of 1s times 1 plus X squared for the number of 2s times 1 plus X cubed and so on. So what does this look like? This generating function will get 1, we'll get X, we'll get X squared, but then there'll be 2 ways to get X cubed and 2 ways to get X to the 4th. Probably should have written out a couple more terms there, or really factors. Right, we'll get X to the 4th just times all 1s, and we'll get X cubed times X. So there'll be 2 ways to get X to the 4th. How many ways to get X to the 5th? Well, I've claimed there's 3 of them. We'll get just X to the 5th times all 1s, get X to the 4th times X, and we'll get X cubed times X squared. Now, so the answer to that question is the coefficient of X to the K in that G of X. And that's really all we can say. We don't have a nice prediction of what that coefficient is going to be. There's nothing that we have right now that gives us a nice formula for that. Let's see. We can use generating functions. Remember the things that were kind of tricky about stuff like occupancy and counting problems when we wanted to throw conditions on there, like the lab partner question, for instance. Now this one isn't quite as picky as that, but how many ways are there to pick 5 letters from A, B, C, D if B, C, and D can be chosen at most once, and A, if it is chosen, must be chosen 4 times. Exactly 4 times. Now, if you just stop and think about this question, it's not a hard question. There's nothing here that you couldn't just do by logic. But that's good because it means we can double check ourselves. So B, C, and D can be chosen at most once. If I'm trying to pick 5 letters, that means I can't do it just using B, C, and D, which means I have to use A. A is going to then be 4 of my choices. So then I get my choice to go with it. I can't use it 5 times, so then I get a choice to go with it of B, C, or D. So the answer is going to be 3, right? But we can look at that another way. We can say in the generating function, g of x, which is, and basically each product in our generating function represents a different choice. So I can choose either 0 or 4, sorry, that should be an x to the 4th, a's, so that's the number of a's. And I can choose either 0 or 1, b, 0 or 1, c, 0 or 1, d. So I can actually write that as 1 plus x to the 4th times 1 plus x cubed. If I multiply that out, and I'm going to actually do it by hand here real quick. So that's 1, oh, that's supposed to be times. 1 plus 3x plus 3x squared plus x cubed. I don't have this one written out, so that's why I'm actually doing math in front of you. So then this will be, well, the x to the 4th is just going to bump everything up, right? So 1 plus 3x plus 3x squared plus x cubed plus x to the 4th plus 3x to the 5th plus 3x to the 6th plus x to the 7th is that generating function. And so we actually can answer more questions than just the one that was asked using this generating function. So using the generating function, we're trying to pick 5 letters. So we're looking for the coefficient of x to the 5th. And that is a 3. You see we get a lot of 3s though. So it turns out that there's also only 3 ways to pick 6 letters from this list. You'll notice there's no ways to pick 8 letters from the list because it didn't say that we had to pick A's in groups of 4, but we could choose at most 4 of them and at most 1 each of these. So the largest number of things that we can get is 7. And so each of these coefficients represents the number of ways to choose 1, 2, however many letters from that set using that rule. And so the rules get handled in how we write our factors in our product, and then the coefficients tell us how many ways we can pick that many things. Let's do one a little more general. How many ways can K indistinguishable balls be placed into P distinguishable cells? And I don't have it in my notes, but I think I want empties to be okay. And actually, let's write it out. I'll write it out for empties okay, and then we'll talk about what would change. Oh, sorry, Alex has a question about the last one. Is 3 because we can have a combination of, yeah, it's 3 choose 2, right? Because we have B, C, or D, and we're going to choose 2 of those. That's why the coefficient of x squared is 3. And so that's actually essentially what it is. It's 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And then to go higher than that, we have no choice. We must have 4 A's, and then of the B, C, and D, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Again. And that's why the coefficients repeat. Also because that's how algebra works. All right, so K indistinguishable balls being placed into P distinguishable cells, and empties are okay. So this is an occupancy problem. This is theorem 210 in your book. We could just look it up. If anybody does, you won't hurt my feelings. We can verify ourselves when we're done. So if we have P distinguishable cells, these are like my colors, or like my choices, how many A's, how many B's, and so on. So I can divide the K balls between the P cells, and I can put either 0, 1, 2, or so on into the first cell. And then into the second cell, I can do the same thing. And so on until I get to cell P, which will also have the possibility of any number of balls being placed into it. So what does this look like? This is my generating function. The answer will be the coefficient of x to the k in that generating function, but that generating function isn't written very nicely. So let's write that as 1 over 1 minus x to the p. Each of these is 1 over 1 minus x because we're allowing it to go infinite, recognizing that if at a certain point the answer is going to be 0 because I'm going to run out of balls I can place. But if I ignore that, those extra balls actually don't matter. If I pretend like I can put 75 balls in, even though K is actually only 3, then it's not going to matter because the x to the 75th term in this thing being multiplied by any of those is not going to change the coefficient of x cubed in that thing. So our generating function is 1 over 1 minus x to the p, and we're looking for the coefficient of x to the k in this. So the question is, what is that? Sometimes the answer is nothing particularly nice, but we know in this case that it should be something fairly nice. This is choosing with replacement, right? And so if anybody's looked it up, this should be something like p plus k minus 1 choose k, something like that. One of those forms, a couple of different ways we could say it. So let's just kind of derive this. We know 1 over 1 minus x is 1 plus x squared plus so on. And so the coefficient of all of these guys, the coefficient sequence is just a sequence of 1s. If I do 1 over 1 minus x squared, then we know this one is 1 plus 2x plus 3x squared plus 4x cubed and so on. And so the coefficient here is just k plus 1. What about 1 over 1 minus x cubed? Remember, we're doing term by term differentiation to go from here to here to here, right? So this is going to be 2 plus 6x plus 12x squared plus, that'd be 5x to the 4th, so 20x cubed, right? And so on. So that's going to be, we had our k plus 1, and then we're going to multiply it by k plus 2. Oh, sorry, no, that's the next one. Hang on. Let's see. This is, yeah, this one is k plus 1 times k plus 2, isn't it? So that's 1 times 2, 2 times 3, 3 times 4. So yeah, k plus 1, k plus 2. Oh, I'm sorry. I left off the 2. This is 2 over 1 minus x cubed. Just taking the derivative of this, I forgot about the 2. We get it's negative 2 times 1 over 1 minus x to the minus 3, but then it's then times negative 1. And so this is 2 over that. So to get 1 over 1 minus x cubed, we have to divide it by 2. And those are the triangular numbers, but they're also k plus 1, k plus 2 over 2. And if we did that again, then we'd get 3 over 1 minus x to the 4th. Take the derivative again, we'd get 3 plus 12x plus 30x squared plus 20x cubed. Wait a second. Sorry, 60x cubed. And so on. And so 1 over 1 minus x to the 4th equals, got to divide all of those by 3, so 1 plus 4x plus 10x squared plus 20x cubed. That was the line I read a second ago. And this is k plus 1 times k plus 2 times k plus 3 over 3 times 2. Right, it was over 2 from before, but now we've multiplied by an additional k plus 3 and had to divide by 3. But this is just k plus 3 choose 3. And if we look back at that last page, this was k plus 2 choose 2. And we could have called this k plus 1 choose 1. And we could have called this k choose 0. Frankly, we can call that anything we want. Oh, almost anything we want, right? There's a lot of ways to get 1. But that fits our pattern. K plus 0 choose 0, k plus 1 choose 1, k plus 2 choose 2. And so we posit that 1 over 1 minus x to the p is equal to k plus p minus 1 choose p minus 1. That fits just what we've gotten so far. And in fact, if we use the symmetry identity, so that we write this as choose k, we get p plus k minus 1 choose k, which should check with your theorem 210 or however you have it numbered. And that was the answer to this question back in chapter 2, right? How many ways can we choose, how many ways can we place k indistinguishable balls in a p distinguishable cells, or the dessert problem. What would be different if empties weren't okay? If empties are not okay. Well then, In my
no
g of
zero.
x, I get rid of all of the ones, right? I'm not allowed to choose only 0. So if empties are not okay, then my generating function looks like this. G of x equals x plus x squared plus x cubed, and so on, to the p. But I can just take an x out of all of those, so I get x to the p times 1 over 1 minus x to the p. And so it's the coefficient, let's see, coefficient of x to the k in here. But then that's the same, the coefficient of x to the, let's see, k minus p, right, in 1 over 1 minus x to the p. And so the coefficient of x to the k minus p and 1 over 1 minus x to the p, just using this, so I have p plus k minus p minus 1 over, or sorry, not over, k, choose k minus p. That's p minus 1, choose k minus p. Using the symmetry identity again, that's p minus 1. And then did I say it backwards?
Wouldn't it be k minus 1? Because we got p plus k minus p, so the p's would cancel.
Oh yeah, this is k minus 1. And this is p minus 1. Right?
Yes? No.
That seems weird. If that's the answer we're looking for, though, isn't it?
I don't think so, because it's...
Hang on. When in doubt, factorial it up. P minus 1 factorial over k minus p factorial. And then that'd be p minus 1 minus. See, that's what's weird.
I would say in the previous step before the cross out, the p minus 1, choose k minus p. That p minus 1 should be a k, right? Because
oh, this should be a k. Oh, that's so much nicer.
Yes.
Oh, okay. Yeah, that one should be a k. Yeah. So then k minus 1 now we're okay. K minus 1, choose p minus 1 when we subtract it.
Yeah.
I knew that's what I was going for. All right. I think that's a pretty good spot to end it. I will say that next time I'm going to talk about x to the n rising, and and x to the n falling again. I believe I've defined these before, but we're going to do that, and we're going to lead up to a generalized binomial coefficient. So where we can start talking about binomial coefficients, where the top number is not necessarily a positive integer, just for funsies. So any questions before we get out of here? I did not put a submit option in Canvas. Well, I will fix that. Sorry about that. Let's see. All right. I think you can now get to it by just clicking. Hang on a second. So I edited my homework 8 to be a file submission.
There is now a submit button on homework 8. So,
Okay,
yeah.
Cool. A preferred document type. Not strongly. Word or PDF is better. I mean, if you have it all on one page and you upload a picture page, that's fine. But what I don't want is like 7 different photos. So if you're taking more than one picture, just compile them into a single document. And like I said, Word or PDF works best for me because I'm working at a Windows machine, so I can open Word and everybody can open PDF. I would avoid stuff like Google Docs. I know it's convenient for some devices, but unless you download it and then send it to me, it will send me a link and then there's permission issues, and they've been I've had trouble with them in the past. I've never been super hardcore on the due dates in this class, so of course if somebody is like sends me something and it's not quite right and I can't open it and I say, hey, I can't open this, it's not like you're out of luck, right? So now don't use the corrupted document hack to buy more time. If you need more time, just ask me for more time. Anything else you guys want to know? All right, let me see. Going to the home page now. So let me make a quick note to myself of what I've promised. So I said, we need to know about exam 2. I said I'd give you my lecture notes. And we probably need a homework 9 coming soon. Anything else? Yeah, end of the day today is fine. Tomorrow morning is also fine. I think I still haven't graded the last one I collected from you guys on paper yet. Does that match your recollection, or have I handed that one back?
I don't believe it's graded yet. Yeah, it doesn't look like it.
So yeah, this week I've got a bunch of lectures to make for some of my other classes, and I've got a bunch of grading to catch up on. But hopefully by the end of the week, everything will be all caught up and we'll be in a regular pattern again. I mean, as regular as anything can be right now. So I'm going to keep doing this class by live Zoom for as long as I can. If something happens and I'm no longer able to get, so I'm over at my East Central office, which is my full-time day job, and they have not locked me out yet. S&T would rather I not come on campus because I'm not essential personnel or something. I have to go through a whole request process just to come on campus to make videos and stuff. So I'm going to make my videos here where I don't have to go through any red tape. So long as I can get in over here, I plan to keep doing our sessions live at 10 a.m. on Monday, Wednesday, Friday. I'll need the Wednesday's link. Sorry that it was kind of late coming to you today. I took an actual spring break, like I said at the beginning of class. So yeah, my plan is to just keep doing our class live. I think we're small enough that we're not putting an undue strain on the system. But if something were to happen where I would not get access to this building anymore, then I'll let you know, and things might have to change because my home internet is crap. And so I don't know that I could do Zoom from there.